Here is a fluid, seen from above, stirred steadily at one length scale, and then left alone. Watch it, because in about 10 seconds I'm going to take it away from you. Because this is what an experiment actually gets. 8 probes by 8. 64 numbers. At each dot, the vorticity. Between the dots, nothing at all. So, from those 64 numbers, can you put the whole flow back? Not something that looks plausible. The actual field, the one that genuinely satisfies the equations of motion. For a long time, the honest answer has been, partly, and it gets worse the more turbulent the flow is. A paper this year moves that answer by 2 orders of magnitude, without adding a single probe. What changes is not the data. It is the coordinates you search in. Andrew Cleary, Wang, and Tamer Zaki, at Johns Hopkins and San Diego State. This is the flow the paper studies. 2-dimensional turbulence driven by a force that varies like a cosine across the box. Omega is the vorticity, the local spin of the fluid. That is the entire physics, and nothing in this paper approximates it. The estimation problem is posed as a minimization. Guess an initial vorticity field, run the equations forward from it, and predict what every probe would have read. Compare that against what they really read, square the difference, and add it up over every probe and every instant. That sum is a cost, small when your guess would have produced the data you actually saw. So the whole job is to make it small. And it is a badly ill-posed job. At the resolution the paper runs, 64 probes are being asked to determine 16,000 unknowns. And the flow is chaotic, so an initial guess that is merely close does not stay close. It becomes a different flow. Before we can even write the tool down, the paper switches notation on us, and it is worth doing that switch slowly because everything afterwards is written in it. First, the stream function. In 2 dimensions, an incompressible flow has a useful property. Instead of tracking 2 velocity components, you can carry a single scalar function whose derivatives give you both. That function is called the stream function, written psi. Differentiate it one way and you get the horizontal velocity, the other way, with a minus sign, the vertical one. And its Laplacian is minus the vorticity, so psi and omega carry exactly the same information. One note on notation while both are on screen, because it will matter later. Bold U is the velocity as a vector, and plain U is just its horizontal component. Same letter, 2 different objects. Second, a piece of shorthand. This bracket, J of A and B, is just a particular combination of first derivatives. It turns up constantly in 2-dimensional fluid mechanics, and it saves a great deal of writing. And here is why it matters to us. Substitute the stream function into the advection term we already had, and the whole thing collapses into minus this bracket of psi with omega. It is not a new term. It is the term from equation 1. Wearing the notation, the next equation is written in. Now we can write down the tool. The standard method is adjoint-variational data assimilation, and it is a gradient descent. To step downhill, you need the derivative of the cost with respect to every one of 16,000 unknowns, and you cannot get that by running 16,000 simulations. The adjoint method gets all of them from one extra solve, and these are the equations it solves. Look at how much of this you already recognize. There is the same bracket, now acting on a new field, omega dagger. There is the same viscous term with the same Reynolds number. The genuinely new things are 3. Tau is time running backwards from the end of the observation window towards the start. This solve marches from the future into the past. Omega dagger is the field it returns, the adjoint vorticity. Psi dagger is its partner, inherited from the constraint that ties vorticity to the stream function. And be careful here, it is not simply the stream function of omega dagger. The second equation couples it to the flow itself. And on the right-hand side, where the original equation had a forcing, this one has the measurement mismatch. That is what drives it. So where does that pair of equations come from? The paper states them and points at an appendix. And I think that is worth undoing because this is the same argument behind every adjoint method you will ever meet. And the force version, the one with things on the right-hand side, is exactly where people lose the thread. Start by noticing that we are minimizing subject to two constraints, not one. The flow has to obey the vorticity equation, and the stream function is not free either. It is tied to the vorticity by that Poisson equation. Attach each constraint to the cost with its own multiplier. Omega dagger multiplies the flow equation. Psi dagger multiplies the Poisson equation. Those two multipliers are the adjoint fields. That is where they come from, and it is why there are two of them. The round brackets here mean integrate the product over the box and over the whole time window. Now, one trick applied 3 times. Every term in that bracket has a derivative sitting on omega, and we want them all sitting on omega dagger instead, because it is omega we are about to vary. So integrate by parts. In time, which leaves a boundary term at each end, and hold on to that, it becomes the whole payoff. In space for the viscous term, twice, and the edges vanish because the box is periodic. And once more for the advection, which picks up a minus sign. Collect everything that multiplies omega into one bracket. And this is what the Lagrangian has become. Now look at where the physical forcing went, the cosine that stirs the flow. It sits off in its own term because it contains no omega at all, so it never reached the bracket. And that answers a question you might have been holding. The forcing that drives the flow does not drive the adjoint. It plays no part in these equations whatsoever. Now vary omega and set it to 0. The bracket has to vanish, but not on its own because the cost depends on omega 2 through the measurements. So its derivative joins the party. Multiply through by -1 and flip the time direction by writing tau for t minus t. That is equation 3a, exactly as the paper prints it. And there is the answer to why these equations are forced at all. The right-hand side is the derivative of the cost. The cost only knows about the flow where the probes are, which is exactly the fact the rest of this video is built on. Do the same for psi. This time the advection term is rearranged a different way, and this is the step that actually needs the anti-symmetry of the bracket, not the earlier one. Set the variation to 0, and out comes equation 3b. And that also explains the one term in 3 that looks like it wandered in from nowhere, the plus psi dagger. Omega appears in the Poisson constraint as well as in the flow equation. So the multiplier belonging to one constraint turns up inside the equation for the other. The two adjoint fields are coupled for the same reason omega and psi are. One thing is still left over, the boundary term from integrating by parts in time. At the far end, there is nothing constraining the solution, so we are free to set omega dagger at time t to 0, and that kills half of it. What survives is omega dagger at time 0 multiplying omega naught, which means the derivative of the cost with respect to the initial field is exactly omega dagger at time 0. That is equation 4, and we did not have to assume it. And notice what we just did. We chose the condition at the end. That is why this thing is solved backwards. Its data is given at the final time, not the initial one. So, one extra solve, run backwards, and you hold every one of the 16,000 derivatives at once. That is the whole reason anybody uses this method. All of that is in the paper, but it is in Appendix A. If you go looking for it in Section 2, you will not find it. So look at what drives that backward solve. The adjoint equations are forced by the mismatch, and the mismatch lives only where the probes are. The probes are points, and a point source has one very inconvenient property. Break it into waves, and every wavelength is present in equal measure. The Fourier transform of a spike is flat. And this is the paper's own measurement of exactly that. On the left, the spectra of the initial adjoint field. The blue curve is state space, broadband, energy at every wave number the grid can hold, right out to the smallest. The red curve is the same correction expressed through the decoder, and it falls away by many orders of magnitude at high wave number. The contour plots beside it are those adjoint fields themselves. The state space one is visibly speckled with the signature of the sensor locations. Do that 500 times, and here is what you get. Panel A1 is state space assimilation from interpolated data, covered in structure that is not physics. It is an artifact of where the sensors happen to be. Panel C on the right is the truth, with the sensor lattice drawn on it. And underneath each field is its entropy spectrum against the true one in black, where the colored curve sits above the black one. The method has invented small scales that were never there. The last panel, boxed in gray, is what we are working towards. Here is the idea that fixes it, and is a change of variables. Think of every possible vorticity field as one point in a space with 16,000 dimensions. Almost none of that space is turbulence. The fields a real Navier-Stokes flow ever visits lie on a thin sheet inside it, called the attractor. And that is what went wrong a moment ago. With 64 numbers, there are enormously many fields that reproduce your data equally well, and almost none of them are anywhere near the sheet. A search over the whole space has no reason to prefer the one that is. So teach something the shape of the sheet. Train an autoencoder, a network that squeezes a flow field down to a short list of numbers and expands it back. The list is the latent representation, ETA. The half that expands is the decoder. The paper uses one with plain linear layers at its narrowest point, which pushes that list to be about as short as it can be, 1,024 numbers. And here is the whole method in the author's own diagram. The blue box on the right is the classical loop you already know. A field, a forward simulation, an adjoint simulation running back, and an update to the field. The orange box on the left is what this paper adds. The latent vector, the decoder that turns it into a field, and the transformed adjoint that comes back the other way. The gray arrow is the old loop. Everything orange is new. And now, the one move of the entire paper. Do not optimize the field. Optimize the short list. Here is the cost function again, with the forward solve written out. And here it is in the new coordinates. The same expression, one substitution. Wherever the initial field used to be, decode the short list first. I want to be exact about what did not change, because this is where people assume the physics got replaced by a network. It did not. The decoder fires once, at time 0, to turn the list into a field. After that, every time step is Navier-Stokes. The authors are explicit. The estimated trajectory satisfies the equations exactly, and there is no learned model of the dynamics anywhere in the method. To descend on the short list, you need the gradient with respect to the list. And that is the chain rule and nothing more. The gradient with respect to the field times the derivative of the field with respect to the list transposed. Now, the initial field is not a free variable anymore. It is whatever the decoder produces. So that middle derivative is the derivative of the decoder's output with respect to its input, which has a name, the decoder's Jacobian. And the right-hand factor we already have, it is the adjoint field the classical method was computing all along. So the latent gradient is the state adjoint pushed through one extra matrix. That is the entire algorithmic change. And that transpose is doing something geometric, which is the part worth understanding. The authors expand the decoder to linear order and observe that each column of its Jacobian is a direction you can nudge the field in and, to first order, still be on the sheet. Multiplying by the transpose projects the correction onto those directions and discards the part that would have walked you off. That is why the broadband junk disappears. So, the numbers. 128 squared and 512 squared. 3 Reynolds numbers, 10 independent trajectories behind every entry. Relative error at the end of the observation window. Classical assimilation started from interpolated data, 15% at Reynolds 100. The super-resolution network on its own is worse still, 60%, because nothing constrains it to obey the dynamics. Use that network to start the classical method, and you get 1.6, and assimilating in the latent space, not 0.28. 2 orders of magnitude over the classical method. Roughly 1 order over the strongest thing anyone had in state space. From the same 64 probes. There's a cleaner way to say what actually changed, and the paper gives it in its last section. It is about observability. Start by giving the thing being solved for a name. Let W be the deviation of the guess from the truth. Subtract the true trajectory from the guessed one, and almost everything cancels, but not quite everything. One term survives that is quadratic in the deviation, and the paper drops it. That is what makes this the linearized Navier-Stokes equation rather than an exact one, and it is worth being straight about. Everything that follows is exact for this linear problem, and an approximation to the real one, good while the deviation is small. Next, rewrite what a measurement is. Define the inner product of two fields as their product integrated over the box. Then a probe reading is exactly the inner product of the field with a spike sitting at that probe. The spike picks out one value and discards everything else. But hold on. The cost we wrote at the start was about the whole field omega, and I have just switched to the deviation W. That step is worth doing properly because the paper does not do it for you. The data you hold is the truth read at the probes. So the mismatch is the reading of the truth subtracted from the reading of your guess. And because reading probes is a linear operation, that is the same as reading the difference between them, which is W. And reading W at one point is exactly an inner product of W with a spike. Put that back into the cost, and you get the paper's equation 12, the sum of squared inner products, one for every probe and every instant. Now, the whole section turns on. Call the forward operator script L, the thing that takes the initial deviation and marches it to time Tn. Then the measurement is the inner product of L applied to W0 with the spike. And an operator has an adjoint defined by exactly one property. You may move it from one side of an inner product to the other. If you have met the transpose of a matrix, this is that for operators. Nothing deeper is going on. So move it across. The measurement is now the inner product of the initial field, the unknown at time 0, with L adjoint applied to the spike. An L adjoint applied to a spike is something you compute once and keep. Release a delta function at that probe. At that instant, integrate the adjoint equations backwards to time 0 and store the field that comes out. That is the adjoint field, and there is one for every probe and every measurement time. Stop and look at what that says, because it is the sentence worth taking away from this whole video. Every measurement you have is one inner product of the unknown field with one known, precomputable field. The adjoint field is not a step in an algorithm. It asks the question that probe asked of the flow. With that substitution, the rest is bookkeeping. But there's one line the paper does not write, and it is the line people stall on. The derivative of a squared inner product with respect to the field gives you back twice the inner product times the other field. That is all. Apply it term by term, and the gradient is a weighted sum of the adjoint fields themselves. Differentiate a second time, and the Hessian is their cross-correlation, the matrix of adjoint fields times its own transpose. That is the machinery. Now watch what it tells you. And that middle line has a consequence people often miss. The gradient is assembled purely out of adjoint fields, so any single step can only move your estimate inside the space those fields span. The span does shift as the estimate moves. The adjoint fields are recomputed each iteration, but it is never the whole space, and it is always built from the same spiky ingredients. And that lets us finally name the picture from earlier. The cost is 0 exactly when the deviation is orthogonal to every single adjoint field, which is to say, when it lies in the null space of the Hessian. So the family of fields that all fit your data perfectly is not a metaphor. It is a linear subspace, and it is the null space of this matrix. A few hundred probe readings simply cannot span 16,000 unknowns, and every direction left over is one your instruments are silent about. So here is the test the paper runs, and it is the cleanest statement of the whole result. The Hessian's eigenvectors are those directions, and its eigenvalues are literally how loudly the data speaks about each one. So order them by eigenvalue, largest first. Take the first eye, write the true field in that basis as well as you can, and measure how much is left over. And this is that plot from the paper. Green is the state space adjoint basis. Red is the latent one, and the vertical axis is the fraction of the true field still missing. At Reynolds 100 directions leave 75% unaccounted for in state space and 20% in latent space. 500 directions, 50% against 5. The 3 panels on the right are the reconstructions themselves. The state space one's still speckled, the latent one almost indistinguishable from the truth beside it. And the reason that second basis is better is the argument from earlier, now with the algebra attached. Because the decoder was trained on field from the attractor, moving a small step in latent space, and decoding lands you back on it. Expand to linear order, and the columns of the decoder Jacobian are precisely the directions that stay there. So the update actually applied in state space is the ordinary state adjoint, hit by the Jacobian times its own transpose. That object is a projector onto the sheet's tangent space, and what it removes is exactly the part of the correction that pointed off the sheet, the part built out of delta functions. Same measurements, same physics, a different set of directions to spin them on. That is the sentence the whole paper is built on. So let me say it plainly. The probes did not change. The data did not change. What changed is the basis you expand in. Observability is not a property of your instruments alone. It is a property of your instruments and your coordinates together. The honest limits, and the authors state them themselves. At Reynolds 400 the advantage narrows, still a real gain, but no longer an order of magnitude, because a busier flow needs a longer list to describe it. And this is two-dimensional turbulence with synthetic measurements. Real experiments are three-dimensional and a great deal messier. But the idea travels further than the example. Anytime you fit a physical model to sparse data, and that is most of experimental science, you're choosing coordinates, usually without noticing you made a choice. What this paper says is that the choice can be worth more than the instrument.